Hello everyone, this is our first video on a new playlist called Machine Learning. Machine learning is the hot topic these days and has been for quite a while, and it is growing at a very fast rate. The jobs in the market for machine learning are growing at a very significant rate, and it is expected that the number of jobs in the near future the job market for it will be basically several 10 millions, like 50 millions or something like that very soon. So it is a hot topic. Many people are using it, from the finance world to the engineering to medical to so many applications, even for entertainment, for chess, for so many different things. The people in like casinos and so on, they always been using it. So in this first video, we are going to talk about what is machine learning and learn about three major types of machine learning: supervised, unsupervised, and reinforcement learning, and several important algorithms. Just in brief, in the next two videos, I'm going to talk about terminologies, important terminologies in machine learning. And later on, we're going to go and focus on each and every one of these algorithms, how to implement them. So machine learning, what is it? It is basically, if I just quote it from Wikipedia or some other website directly, I would say it is basically a study of algorithms, you might say computer algorithms, that try to improve themselves, try to improve their performance through dealing with data and through learning from data. So not every single detail of what, let's say, you want your robot to do is going to be hard programmed into the controller of the robot. You let the robot basically interact with the environment, for example, and learn, right? That's like a machine, like a reinforcement learning. Or if it's not a robot, it's just some algorithm in the computer, right? You would allow it to dig deep through the data and then try to learn through the data some models of the environment, right? Some patterns of the data and so on. So without you programming everything to the finest details, you let your algorithm do that, just like us humans. Not every single thing of what we do in daily routines is being instructed to us. I mean, when we're growing up, definitely our parents give us some details, some instructions, but as we grow up, we learn by observing and making models of how the world works, right? The world, and we try to learn ourselves through interaction, observation, and through basically the data that we get from the world. That's the idea of machine learning, to act like humans, make the algorithms, make the robots act like humans. So there are three main types of machine learning. One of them is called supervised learning. Here, not only you give to the algorithm or robot the inputs, you also give it the desired or labeled or tagged outputs or tagged data, right? And then what? Then you ask the algorithm to find a relation between the inputs and these desired outputs. For example, in one of the most common algorithms or methods of supervised learning, which we call regression, you are going to give it a bunch of X and Y data, and you expect your algorithm to find the underlying function. Let's say here, for example, are what? These are, let's say, some data of, for example, let's say if I want to make it in the world of engineering, these are the force of a spring versus the deflection in the spring, right? So if you have done the hooks experiment, you're going to get a bunch of these red squares. These are the forces and the deflections of the spring, and say, hey, could you find a relation between these data? I have no idea what the underlying function might be, or I might give you some hint, say this is a polynomial or something, but could you find an underlying function for me? And then the regression analysis tries to do that, okay? So for example, if you say polynomial, then it finds that maybe the best polynomial is a line here, right? Or maybe it's some other function. So this is a regression. And once you build the model, now if I give you a new point and say, hey, I'm going to give you a new point now, if I try my spring at a new location, at a new deflection, let's say here, what is going to be the spring force? So I give you this delta, and I say, what is the spring force? Okay, so when you use regression now, when you build up this model, this line, now for any desired input, you can find the corresponding target or the output, right? So that is the regression problem. The output is always a numerical value. That's a regression. On the other hand, we have something similar, but also quite a bit different, called classification. In classification, you still try to make a model out of the what we call training data, by the way. So let me emphasize on this word. By training data, we mean all of the sets of inputs and desired outputs that are given to my algorithm. So from this training data, we are trying to basically classify the data into specific number of classes. For example, I give you these images of bananas, peaches, and apples, and say, hey, these images belong to bananas. So these are my inputs. And then the label or the output for it is banana. These guys are peaches. These guys are what? Apples. And now say, okay, could you make a model so that based on these pictures, if I give you a new picture, you can tell me what class of these three objects that one is. And if it can do it and say, yeah, that is the picture of an apple, then you say, yeah, I've made a good model, right? How? There are different ways to do it. One of them that we are going to see is neural networks, artificial neural networks, which is a very big topic in machine learning, especially the new side of it, deep learning, which we'll discuss in future videos. But in classification, the goal is not to come up with what? With the numerical value as the output, is to come up with a class. So here, if I want to say the output is a numerical value, here the output is a class. Okay, so these are typically disjoint classes. You have a finite number of them, while in regression, this is a numerical value. It can go over even a continuous range. Okay, these are two main categories of supervised learning, regression and what? Classification, where both inputs and the outputs or label data for outputs should be available to the machine. What's the hard part about the supervised learning? The hard part is this part, labeled or tagged data. It's always easy to get a lot of labeled or tagged data, right? Let's say, and we're gonna again talk about it, but let's say you want to create a model for this classification problem, that if I give you pictures of bananas or apples or peaches, you tell me which category it is. So one of the main algorithms for doing that, one of the main methods in machine learning is neural networks. So if you want to do that, you need to pass tons and tons of pictures of apples, peaches, and bananas to this machine. So the model it makes for predicting the class of the new picture is very robust. Why do I need a lot of data? Because guess what? These bananas, peaches, or apples comes in tons of different shapes and colors. Not only this kind of red, beautiful apple is apple. The apple could be green, could be yellow. Part of it could be eaten, right? It could be sliced. It could be rotated, not like this. This leaf could be down here. It could be big. It could be small. The image could be high quality, low quality. There could be spots on it, right? So with all of those variations, if I just choose a few pictures and say, hey, maybe the model is as simple as what? Look at the color. If the color is red, then definitely it's not a banana. And then now maybe you look at some shape like roundness of the shape, right? Apples are not round as much as peaches are, but who knows, you can get an apple that is quite as round as a peach. Or maybe peaches, they have this red component less than or more than the apples. It's not that reliable. If you want a reliable model, you need lots of observations, a lot of data to make a reliable model. And guess what? Somebody needs to sit down and look at each and every one of those thousands and millions of images you bring in and label them. Tell the machine, hey, this is apple, this is peach, this is banana, and keep going. Right? And imagine instead of 3 classes of fruits, you have maybe 100 classes of fruits, right? Just imagine how much work is going to go into labeling your data and giving it to computer. So getting a lot of labeled data is a very expensive thing. This is very expensive and time consuming. It's not always available to us. It's a fancy thing to have millions of images of fruits with label and everything. Not always you can do that, although these days people are making more and more of what we call databases, but still it's not always possible. The good thing is, because you have the desired output, if you have enough of them many times, if your algorithm is good enough and chosen properly, you can make some good, reliable, robust models. And now one of the famous examples of this classification thing is Google Lens, right? This is the app that you can add to your cell phone. And basically what it does, you just give it a picture that you might take right off the bat with your cell phone, and it looks through tons and tons of the images that Google has. Of course, it doesn't go through each and every one of images. It does use some machine learning to narrow it down to the categories they are closest to, and then finally give you an answer. Hey, this picture that you took is a tulip, right? Or if you see some text, it tries to do text recognition for you. Say, hey, this text is what? For example, it is saying this, right? And that's one of the things that you see I have provided the picture for, text recognition, which we do with neural networks or with other algorithms. So we get to it. So we said the 2 major things are regression and classification under supervised learning. Now, some of the well-known algorithms under this category are linear and logistic regression. This, what you see here, is linear regression, okay? You see clearly I'm trying to pass a linear function, linear polynomial to my data, but linear regression does not necessarily only mean linear polynomial. When we say linear regression, it means the regression function in terms of its parameters have to be linear. Not that the function itself is necessarily linear. Okay, there is some big difference there. So let me tell you. For example, Let's say if I have a function y equal a times x plus b, right? If I have my data xi and yi, which are known values, and I write it like this: a times xi plus b minus yi equals 0, right? And then I have another one, let's say axj plus b minus yj equals 0. So here I can write this relation into a matrix format and say what? Say xi and 1, xj and 1 times a and b is equal to yi and yj. So in terms of the unknowns, I could write the system into a linear set of equations. You see, I could use matrices. Here the function was linear, everything was fine. But you might say, well, is that the only thing? No. If my function was a little bit different, like what, for example? The function between y and x was nonlinear, but I could convert it into a linear relation in terms of parameters, like y equals, for example, e to the ax plus b, right? Now what? This is clearly a nonlinear function between y and x, but if I take natural log of both sides, and now if I write this relation one time for xi and yi and the other time for xj and yj, guess what? I can still convert this relation into a linear set of relations. Again, it's going to be xi and 1, xj and 1, a and b. Now the right hand side this time is going to be natural log of yi and yj. But still, in terms of these unknowns, the relation is linear. So this function counts, the regression that I'm doing, the curve fitting that I'm doing, counts as linear regression, okay? So this is linear regression. Write the relation between input and output as a function in which you can arrange it, rewrite it into a matrix format, a linear format in terms of the unknown parameters, and then find the unknown parameters, so now you have the underlying function. This is linear regression. And the application of it is very clear: to predict the numerical value at an unknown what? At a known input. If you want to find the output at that known input that is not in your training set, if you want to find that output for it, for this new input, you can do it, right? You can give a numerical value. In logistic regression, the type of function that you use looks a little bit different. It's called the sigmoid function. The sigmoid function looks like this. Okay, it is kind of similar to a tangent hyperbolic function, and they are related actually. So this is called a sigmoid function. What's good about this function? The good thing is, at small values, we can approximate this by this. We say at small values, it is one function with one level. Then it jumps to what? Higher values, and at higher values is another plateau, another level. So I can say, if I have some data here, or some data there, right? Maybe I have some data here in the middle too, but if this transition is not that wide and is quite a sharp transition, then I can say, I can use it for also classification, and I say, well, the output is either this level or it is what? This level. So I can, if they are numerical values, I can directly use the numerical values, or I can also use them for classes. Say, hey, this is class 1 if the output is this much, and if the output is this much, then it is what? Class 2, right? So if I have some new data here, I project it onto the sigmoid function, and the output is very close to the class 2, so I can say that belongs to class 2. So I can also use linear regression for classification too, not just regression. Give the numbers here. If I consider only 2 classes here and ignore this middle area, or this middle area to whichever class it's closer, I assign it to that class, then I can use it for classification too. So that's called logistic regression, and logistic regression is a regression that uses a what? A sigmoid function. Okay, so far I explained to you 2 of these well-known algorithms in very brief detail. Of course, we have not talked anything about calculation or so. I will go in separate videos over each and every one of them. I'm just trying to just briefly tell you what they are. Artificial neural networks, or neural networks, are the algorithms in which they are trying to mimic what is happening inside human brains. Okay, so they are trying to find relations between inputs and outputs by doing something basically similar to what humans do. What humans' brain do, they have neurons, and these neurons are connected to each other, right? And they get some inputs, and then based on the level of inputs, they generate an output if the input is at a specific level or above that level, right? So they have some thresholds. They have some what we call firing thresholds. So if the output they generate is below some threshold, they don't generate an output signal. If it's above or at some level, they generate an output signal, an electric signal that goes to another neuron, right? So this neural networks, what they are, you give them all of these inputs to an input layer to process it. They generate some outputs based on these inputs, and they pass those outputs to another set of neurons. And then again, this work is repeated, goes from one layer of neurons to another, until they finally go to the output layer of neurons. Okay, and now what would you do? So first of all, the first layer that you pass the input to, you call it the input layers. The last layer that you get the output from, you call it the output layer. And any layer between the output and input, you call it the hidden layer. Okay, we talk about neural networks in several videos in the future, because neural networks alone is a course by itself, is a graduate level course. I remember I passed it so many years ago, and it is a course of its own, but I'll try to cover it with as many videos as I can. Okay, so we are going to stop on this topic and cover it in several serious videos. But and by the way, because you heard probably this term deep learning. Deep learning is when you use a lot of basically these hidden layers. When you use lots of these, that's the idea of deep learning. Now, it has a little bit more than just adding tons and tons of this, but that's the overall base idea of they are, because many of the neural networks that were used in the past, they did not have a ton of layers and a ton of neurons in each layer. But now, because the computation power of us has increased significantly, and we have tons and tons of data to train these massive networks with, this allowed us to use more and more layers and more neurons, and basically it is discovered that these deep big networks can do a lot more fascinating jobs and many tasks we could not do amazing in the past. Now these guys can do it, and that's what our brain does, right? You know, our brain has as far as I know, a couple of 100 billion neurons, right? So, but brain is extremely efficient computer. So because we have lots of data and what? Fast processing. These are available to us these days. We can afford to do that. Now in neural networks, when you go from each layer to the next, the data is changed. Okay? One of the simplest thing you can do is you can multiply, let's say, this input, if you call this x, you can multiply it by a gain, a weight, like w. So the data that goes here is like x times w. And then here you can pass it through a function, which is called the activation function, right? So maybe here there is some function like f, as well as some new gain, like if you call this w1 and then call this w2, and there is also some function here like f1. So the data here is like f1 of x times w1, but then the whole thing is also multiplied by w2. And keep going. So you can use lots of different activation functions and lots of different weights. The activation functions are fixed. You're not going to change them. But these weights, these w's, you try to change them in a what we call an iterative manner or in a loop, and you change those such that for the data x, if it's the input, it gives the corresponding what? Output that you want, the target data or the desired output for it. So initially, if you just start these w's with some random numbers, the output here is definitely, if you call this output whatever you want, a, this a in the beginning is not going to be equal to the desired y that you want. But you keep changing these w's until ultimately the output that comes is equal to your desired output. And that's where you say my network is trained, the system has converged. Okay, so basically what this is, in that sense, this is like a fancy regression, basically. It's like a complicated regression with lots and lots of unknowns. Remember here, I only use two unknowns, A and B. Here, you might have thousands of these weights, W's, and some other parameter called the bias. We'll talk about it, right? So in that aspect, this neural networks could be a fancy regression algorithm. But it turns out it's not just that. Neural networks can do a lot more than just fancy regressions, okay? They are used in lots and lots of different areas of machine learning. In unsupervised learning, we use them. In reinforcement learning that I'm going to explain to you, we are going to use them. So although here I mentioned neural networks as under the category of supervised learning and mostly used for regression, or maybe, regression, or you can also use them for classification. If this output is not a number, it's just a binary number showing the class, that could also be used for classification. So this has covered both of these, and as I'm going to tell you in the future, it can also do unsupervised learning, which is like data clustering, reducing the size of the data, dimensionality reduction, using what we call autoencoders. And then there is this reinforcement learning where they combine with Q-learning, call it deep Q-learning. And there are so many areas that these neural networks shown very, very powerful and useful. So it's way beyond some very fancy regression or function estimation. What else do we have? We have decision trees. Decision trees are very similar to the 20 question game that you might have played, right? For example, somebody gives you a question and say, hey, with 20 questions, you tell me that what kind of animal it is that I have in mind. So I tell you it's an animal. You tell me with 20 questions whether you can guess what animal I have in mind. And then you start asking question, hey, does your animal have feathers? Right? And then it says true or false. Then you say, well, if it's true, now I would say, can it fly? If it say yes, then there are tons of birds. Maybe one of them is a hawk. If it's not, maybe it's what? Maybe it's a penguin, maybe it's an ostrich or so on. And then if it cannot fly, then you say, hey, does it have fins? And if they say yes, it might be a dolphin, some fish or something. If it's not, then you might say it's a bear, or you have to keep asking more and more questions, right? So you keep going until you narrow it down to a case that the probability of your answer here is about 100%. So you're not guessing anymore. But you have to do it with only what? With 20 questions, because here you have asked question 1, here you have asked question 2, right, for this category. Then you have to go with question 3. And with a limited number of questions, your goal is to narrow it down to a case where you are 100% sure about what you are going to answer. This is called the decision tree. And in the decision tree, the major thing is what questions to ask and where to ask them. Like, should I ask whether it has feathers right off the bat, or maybe should I ask, can it fly right off the bat? Right? Where do I put these questions and what type of questions to ask? That's the major thing about decision trees. And you have seen this a lot maybe these days online. You might say, like, where? Like, for example, you go to some of these websites and they say, well, we are going to guess your education level, or we are going to give you a price for your car or your house. But you first answer a bunch of questions for us. And that's exactly what they are doing, right? They know it's a house you're going to sell and they want to give you a price. And now, based on a lot of observations and a lot of training data, they have figured out a model, and the model is where to put these questions and when to ask them, what kind of questions to ask. So with a limited number of questions, they are going to give you a relatively good price with a good probability that it's not over or underpriced. Okay, so you have seen this decision trees, and since I'm at decision trees right now, before I go to support vector machines, I would like to talk about random forest because it's very much related to decision trees. So let me talk about this right here. What is a random forest? A random forest is what we call an ensemble learning method. What does ensemble learning mean? It means it's an algorithm that itself uses several other algorithms, and it tries to use the result of all of those and then come up to maybe a majority voting or an average or something like that to give you what? To give you a better answer compared to each and every one of them, right? So it's like a democracy machine learning thing. It is asking several different algorithms to give their vote to maybe what kind of class of data is this before it gives you a final answer. So now if you use several of these decision trees, right, with different location of the questions, different type of questions, and different number of them maybe, and each one of them give you a separate final answer, of course, then you take an average or a majority voting or anything depending on the type of the problem, whether it's regression or classification, right, then you can have a random forest, okay? So, by the way, this decision trees is something that you can use both for regression and classification. So just wanted to mention that. Okay, what else do we have? one of the other algorithms under here is called support vector machines, or SVMs. What are these? So these are also the problem of classifications, but the goal of SVM is to find the best separating hyperplane for the classification. What do I mean by that at all? So let's say here you have a bunch of data, but these data are in two different classes, circles and triangles, right? Now, if somebody says, how can I know if I give you some new data like this, whether this data should be called, maybe let me use a square or something, if this data better be called based on the position of that in this what we call a feature plane, based on the values of that, coordinates of that, is it better that if I count it as the triangles or I count it as the circles, right? Well, there are different ways to do it, and one of them actually is going to be related to my next algorithm called k-nearest neighbors, or KNN. So, but let's first talk about the support vector machine. So what does the support vector machine says? It says, well, I try to draw a boundary, a separating plane, if it's multi-dimension, so you have more than 3 dimensions, right? Here, each point, each data has only 3 values associated to it, or 2 values, right? Or if it's 2 values, your separating boundary is called what? A line. If you have also a z, then each data from the other data can be separated by a plane. If you have more than 3 data, or the dimension of the features of your data point is more than 3, then we call it a hyperplane, okay? So it says I draw a boundary for you. And this boundary on one side of it is going to be one category of data, on the other side is going to be what? The other category of data. But you might say, well, not only that line works, because that line clearly separates the 2 classes of data from each other. How about this line here in green? Do you think this line in green also works? Let me draw a little bit better, something like that. How about that? You might say, well, why not? I say, well, how about this one maybe in, let me use a different color, orange. How about this one? Is this guy gonna work too? Well, of course, for sure. Why not? So, and then they might say, well, now which one of them should be used? If there are so many different ways that, right, let me show another one. If there are different ways, different hyperplanes to separate these data from each other, which one of these different lines, or in general hyperplanes, is the best one to separate? And the goal of support vector machine is to find the best one. Now, what does best mean? Best means it has the maximum, what we call margin, from the data or for the data. And what does that mean? Well, let me show you. So here, let me get rid of these. So here, if you look, if I draw a line parallel to this black line so that it comes almost in contact with the circles like this, and then draw another parallel to this so that that one almost comes into what? Into contact with the triangles, right? So let's see if I can get it as wide as I can, something like that. Good. So now you see I have some big gap between these 2 supports. By the way, each one of these walls is called a support vector. Or the normal vector to each one of them is called the support vector. So here I have some big gap between them, and that's the meaning of margin, correct? While if I have done this with a separate set of lines, let's say this time I use the green line, but I change my green line to maybe this one. Now what? So this is almost at the boundary, right? Because you see it's almost touching one of the triangles. And now if I try to make a parallel version of that, you see the parallel version of that, which is almost at the circle, cannot be so far off from this one. Look at this. You see? So if my original line, original green line, is somewhere between these two, let's say here, see if I can do it here, right? So this bigger green line is the original line that I drew instead of this middle black line. And then these are the parallels to it at the boundaries of the objects, I mean, beyond which you will have misclassification. Now you definitely see that the gap between these green lines at the borders, the supports, the gap here is much, much smaller compared to the black one, right? So the goal of the support vector machine is to find the best hyperplane, means the one that itself and or its parallels or the support vectors of it give you the largest gap between the data. This is the best classifier, really, okay? So this is called support vector machines. And this is not the only method in machine learning that gives you some hyperplane to separate the data, right? But this is the one that gives you the one with the maximum margin, because there are other algorithms in machine learning that give you a separating plane, right? For example, if the goal is just to draw a plane that separates them, one of the things that can do it is neural networks. Neural network, one of the types of neural networks is called perceptron. And perceptron is a type of neural network that can do this job. The goal of it is to find a separating hyperplane between classes of data, right? So perceptron can do that, but it cannot necessarily give you the best one. Okay, but the goal of support vector machine is to give you the best one. So that support vector machine, now as I mentioned, this classification problem brought up already the problem of nearest neighbor. What is the nearest neighbor? The nearest neighbor is this. If I go back on the same problem I just brought up, and that is if I give you a new data, right, let's say here, and I say, what kind of data is this? Should I call this a triangle or a circle? How would you do that? One of the things you can do is to look around it. To look around it and see the data around it, the data close to it are what type. If most of the data close to it are triangles, you call it a triangle. If most of them are circle, you call it a circle. If it's a mixture, then you have to come up with a decision. And you can see that better in this bottom picture. So I have purple circles and yellow circles, right? Now, if I come up with the new data, this red circle, and I say, do you want me to call it a yellow or a purple? You say, well, I would look in the surrounding of the data, in the neighborhood, right, vicinity of the data, and see what are the majority of the data around it. Now here you have to have a distance for the vicinity, or you have to basically, when you sort the data from the closest to the largest, you have to sort them from smallest to largest and then look only at, let's say, the top k closest data. That's why we call it what? K nearest neighbor. So here k is 3. So I'm looking at the 3 closest neighbor of the red data. One of them is yellow, 2 of them is purple. So I say, well, it seems like the majority are purple, so I would call the red data to be a purple circle. But if I change my k to be 6, guess what? Now I look at the 6 closest circles. Now I have 2 purple versus what? 4 yellows. And now if I want to go based on majority vote, I have to say what? The this one is actually a yellow circle, it belongs to the yellow category. So you clearly see that's another big problem in machine learning is choosing the parameters, choosing the functions that, let's say, you did in neural network. If those activation functions, they change from one function to another, you see huge change in the behavior. Or if the number of neurons or the number of layers changes, you see some big changes. Here, the same thing, K. What K should I choose? Okay, many of these parameters, hyperparameters, and so on, it's not necessarily super easy to just choose. You have to have a way to know when is it that K of 3 is good or 6 is good or something like that. Because as we will see in the next video, we have the problems of overfitting and underfitting. Okay, when is it that used too few parameters? When is it that used too many parameters? Or here a big K or a small K or so. When is it that we should really stop and say this K is good? Okay, so we'll talk about those problems. But anyways, this is the essence of K nearest neighbors. Based on the majority vote of the K nearest neighbor, we classify a data as belonging to one of the different classes. Okay? And finally, we have the naive Bayes classifications. Okay, so for this, you have to know the Bayes theorem, which we'll talk about in the next video. And naive, as you know, means they are not necessarily the smartest. So what is this? First of all, as the name says, it's a classification algorithm. Okay, it is a classification algorithm. It is using the Bayes theorem. That's why we call it Bayes classification. And naive means what? Well, these different features, these different values that you choose for each one of these points, not always these features are what? Independent from each other. Sometimes you choose like 10 different features to describe the location of one point, but not necessarily all of these n features are what? Independent. Naive Bayes classifier comes and assumes that the features, where is it here? It assumes that the features are independent, which is a naive assumption. In many applications, we can easily show that there is big correlation among these feature values. Okay, but here, this is one of the simplest classifiers, and it assumes independent among the features to make life easy, which of course brings down its performance, but it makes the application of it and implementation of it simpler, right? So it uses the Bayes theorem, and the Bayes theorem says P of B given A is equal to P of A given B, right? Times what? Times P of B divided by P of A. Okay? And the proper interpretation of that will postpone to the next video, but this is what we call the Bayes theorem. And basically, this term here is called the prior probability. This is called the likelihood, and this is called the posterior probability. This is just a normalizing factor that in many applications we neglect. And based on these two terms, it tries to basically estimate the probability that an observation comes from a model. So here A corresponds to the model, and B is the observation. A given B is, if I have some model, what is the probability that some observation coming out of it? So this guy, as I said, if I want to just very fast, briefly tell you, this is called, as I say, the prior probability. what is the probability of the observation, right? And this is called the likelihood function. This is the likelihood that from a model some observation comes out. This is the chance of seeing that observation in general without depending on any model. And then now that I have seen this observation, how likely is it that it has come from this model? Here, instead of model, it could be what? A class. And this observation could be also what? Data. So what's the chance that this data here comes from this class or it comes from this class? Right? So here I have to have these likelihood functions for whether this data is coming from this purple class or the green class, plus the chance in general that any data comes from a purple class or comes from the green class. And of course, if the green class is a bigger class, it has a higher probability that it can give you a data. If the purple is smaller, it has a smaller class. So the size of these two classes are basically this factor prior probability. And as I said, we're going to go through that with examples and everything. But what this naive Bayes classifier is, it is a probabilistic classifier. The previous classification that we have done, like the KNN, right, or for example, the perceptron neural network or something like that, these are giving me a crisp answer. It's class A or class B. This one says, for example, it is probably 60% chance that it is class A, and it is 40%, let's say, chance that it is class B. So it's not going to give you a binary classification, 0 or 1. It gives you a probability that the data belongs to each and every one of the classes. If you want then to convert it into a binary number, you have to do some modifications on it. But this is, in general, what we call a probabilistic classification, and naive Bayes classifier is the simplest of them all. Okay? So far we have seen supervised learning and a few well-known algorithms. Now, unsupervised learning is where that amazing tagged data or the desired output is gone. The only thing you have is the input alone. There is no desired output, only input. So what is it that you're going to do? The goal here is not to find a model or something. The goal is to find patterns or structure within the data without any tags. Like what? Like I give you this data, just a bunch of pictures of fruit, and say, hey, could you find patterns within this? Could you find clusters? That's one of the terms you hear a lot in unsupervised learning. Could you find clusters of data? And by clusters, I mean those group of data that have the highest similarity to each other. And you might say, yes, I can see this is this cluster, one cluster of data. You're not going to call it apple. You never told it that, hey, this is apple. No. It says, hey, I see one pattern, one group of similar pictures. This is another group of similar pictures. This is another. So you say what? I have 3 clusters here of data, 3 patterns, 3 different types of data. This is called unsupervised learning. You never, as I said, told your computer that, hey, this is banana, this is peach, this is apple. You eliminated this portion of the data. Okay, that's called unsupervised learning. So in unsupervised learning, there are different also algorithms, but the major ones, one category of them are clustering algorithms, like k-mean clustering or Gaussian Mixture Models, GMM, as well as some density functions. GMM actually does both. And the other category of unsupervised learning algorithms are dimensionality reduction algorithms. So remember, supervised learning had two major categories. What were they? They were regression and what? Classification. These are the big categories of supervised. For unsupervised, the big categories are clustering and what? Dimensionality reduction. These are the two big categories of unsupervised learning. And what are these? Let's talk about them. So under dimensionality reduction, we have principal component analysis, or PCA, singular value decomposition, SVD, autoencoders, which are a group of neural networks, and so on. So what are they? Let's talk about them. First, let's talk about the clustering algorithms, and one of the most well-known and favorite ones called k-means clustering. There is also k-medians clustering and so on, but k-means is the first one actually that was described. So what is this method? So let me go down a little bit. Here you have a bunch of data. No label to any data or so. What you want to do is to put this data in a bunch of clusters, in a bunch of different bags, similar categories. You determine by yourself how many clusters do I want in the beginning. Say, well, I think I have 4 clusters, right? And then say, where are these clusters, right? You try to basically come up with some center for each cluster, right? And some label for each data, whether that data belongs to a cluster or not. So first you say, well, I think I have 4 clusters maybe. The center of cluster 1 is here, the center of cluster 2 is here, the center of cluster 3 is here, the center of cluster 4 maybe is here. And then through basically iterations and update, you try to basically bring these centroids to their appropriate location. So maybe this should come here, right? Maybe that guy should go there. And then this one comes here maybe, and that one goes there. So you try to make these centroids converge to their best location so that what we call the intra-cluster error or deviation becomes minimum. And that is sum of the squared of deviations from each one of these data to their centroid. Of course, if the centroid of this data is here, when you take some of these squared errors and add them together, that's much smaller compared to where it was at the yellow point. So you're trying to bring down what we call, as I said, the intra-cluster deviation. And so, not only now you know where the centroid of each class is, each data will also be labeled with a number. So if the data is labeled with number 1, that means it belongs to class 1. If has label 2, class 2 or cluster 2, label 3, cluster 3, label 4, cluster 4. So each data will now get also a tag or a label that it belongs to which cluster. Now, did I have any assumption here about what kind of shape each one of these clusters take? No. I don't care. That shape of the cluster corresponds to what kind of distribution that we have in probabilities. No. This is basically a model-free clustering. All you need is the centroid location, the number of clusters that you decide, and whether each data belongs to each cluster or to another. Now, of course, as you guessed, the big factor here is K. If I go with the wrong choice of K here and I say, well, it's just 2 classes, then that's not so easy. Although you will end up probably with something, but it might not be the easiest for this algorithm to end up with some meaningful data. Now, of course, it gives you something, but whether that has any meaning or not, It's not that easy. Maybe if you say I want 3 clusters, then it combines these two together and say this is one, this is one, right? If you say 2, then you have to see whether it kind of break it down into something like this, right, or something different. It all depends on basically where these data are, and it tries to bring down that intra-cluster deviation. But that's the, and we have methods to find the best number for k, which in a video of itself I will describe. K-means, I'll tell you where and how to decide what is the best k. So that's called k-mean clustering. Now, in a separate, similar clustering method called mixture of Gaussians, or Gaussian Mixture Model, GMM, in the GMM, you do have some assumptions on the shape of the models, the distributions of these clusters. You assume that they are Gaussian distributions. A Gaussian distribution in 2D would look like an ellipse, right? In 1D, as you know, a Gaussian distribution is a what? It is a bell-shaped curve like this. But when you look at it from the top and you make it 2D, now this guy will be rotated like this, and then if you just look at the significant area, it is going to be an ellipse. Okay, so an ellipse is like if this is the center and each direction is like 3 sigmas, sigma 1 and sigma 2 that you have away from the center, then you have the Gaussian distribution. So this method here, GMM, has some assumption. It says your data is a mixture of separate Gaussian models. So you have a bunch of different Gaussian models and your data coming from a mixture of them. And then it decides where is the centroid for each one of those Gaussians. And then what? How much is sigma 1 and sigma 2? So let's say this is 3 sigma 2 almost. This is like 3 sigma 1, this distance, and this is like mu, correct? It tries to estimate these hyperparameters for each one of these Gaussians, and now tries to cluster the data accordingly. Okay, so it's called the mixture of Gaussian models, GMM, or other methods of density estimation. So you have a bunch of data, and then it tries to estimate the kind of either kernel density estimations, or if you know the kernel function, try to estimate the hyperparameters and so on and so forth. So these are clustering subcategory. The other subcategory called dimensionality reduction. What does that mean? It means, as I told you earlier, for each data, I use a bunch of what? I use a bunch of values, which we call features, right? Like here, I only have X and Y values for each data, but in many applications, the number of values associated to each data point are a lot. You might have like 100 values, a vector with 100 values for each and every one of these data points. Now, do you really need all of these 100 data values to predict whether that data belongs to class 1 or class 2? Not necessarily. Many of these data have a ton of overlap, a ton of similarities. Some of them are barely any useful for the regression or classification, especially for classifications. So what is your goal? The goal is to bring down, let's say, this 100 by 1 feature vector that you have, reduce it down to maybe only 5 data, 5 values, that if you look at these 5 values, they have minimal overlap, they have minimal dependency, and really by looking at these 5 values, you can correctly tell, or to a good extent tell, whether data belongs to what class. So most of the redundancies in the data you try to throw away and only keep the useful, independent, mutually exclusive part of the data. This is called dimensionality reduction. And there are so many different ways that you can do it. One of them is called principal component analysis, PCA, which basically uses the covariance matrix of all of these random variables and data and tries to find only the ones that carry the maximum amount of information. That's called principal component analysis, right? So for example, if you look at this image, that might be quite revealing. Here you have a bunch of different data, right? Now, here the dimensions are not necessarily reduced. Here your 2 dimensions, you're still gonna keep it at 2 dimensions, but with a twist. What is the twist? So here, instead of me looking at X and Y of each data, I try to come up with some new modified transform version of the X and Y, maybe X prime and Y prime, where if instead of looking at X and Y, if I looked at X prime and Y prime, that could reveal a lot better about my data. Why? Because if I look at my X and Y data, you see that they are big time correlated. Look at them. You see, when X is increasing, Y is increasing. This is big correlation. So it means I maybe just look at X alone. At each point with X, I can guess how much Y is because they are big time related to each other. There is a big correlation. But if instead of X and Y that are correlated, and one of them could be quite useful to some extent, if I rotate my coordinate and look at this X prime and Y prime, then what? If I look at X prime, you see X prime values are kind of independent from Y prime. And Y prime values also what? Quite independent from X prime. So I have 2 independent direction of variation. There is no correlation between X prime and Y prime, while there is big time between X and Y. So instead of X and Y, I use X prime and what? Y prime. Now here, again, I have not reduced the number of features. I went from 2 to 2, but from 2 correlated ones to 2 that are not correlated. That can improve the performance of any classification algorithm significantly. But many times, you go from a lot of these X and Ys to a few X primes and Y primes. Not only X primes and Y primes in PCA have a lot smaller dimension, smaller size compared to X and Ys, but they are also what? Orthogonal, independent from each other. That's the essence of PCA, which we'll address in a separate video of its own. There is singular value decomposition, which is a topic of its own. I have one entire video. I have covered this. If you go to linear algebra playlist of mine, I cover singular value decomposition. And here again, looking at the matrix, we are trying to break it down. A matrix that is not a square matrix. We are trying to looking at the singular values, and then we keep only those singular values that are the largest singular values, and neglect the rest of them, as well as their associated eigenvectors, right? Or U and V matrices, and bring down the size of a giant matrix to a much, much smaller matrix, while still keeping the quality of the data that the big matrix could show. The small matrix can still keep 90-95% of the data of the big matrix without being super large. Okay, I showed, even in that video I published, I showed how you can use this method to compress images. Okay, so instead of a huge matrix, so many 1,000 pixels by 1,000 pixels of one image, you can bring it down to a much smaller size and still compress the image to a much smaller size, yet keep all of the important features of the image. So I'm not going to go over this. Maybe I would talk about it at some point, but I have a complete video on singular value decomposition under playlist linear algebra. Autoencoders are a very smart thing for doing something like PCA. but basically what they are is a neural network. So they are similar to this. What's the why did we call them smart? Because in the autoencoders, the input layer and the output layer are similar to each other. So let's say here, you train a neural network with input and output being the same. So here you have 5 features, here you have the same 5 features. These two are equal to each other. And you train a what? A neural network, then when you give it X, it gives you back X. But using what? Using an intermediate layer of much smaller size. You see here, instead of me storing the information of X with 5 features, I could store it with what? With 2 features, with 2 neurons, 2 weights. So it says to me that these 2 weights with their layer, with their activation function, can give me all the information that was stored in these 5 features. And so instead of now me dealing with this, I can be dealing with what? With this one. Because this has the same information as the input layer. And this is kind of like bringing down what? The number of dimensions. So this is called an autoencoder, which is a really nice thing. So you clearly can see that, as I told you, I could use neural networks for regression. With the perceptron that I talked about earlier, you can do classification and clustering, and you can also use them for what? For dimensionality reduction, okay? So that's why so far we see neural networks can cover lots of different areas of machine learning. That's why they are so powerful and such a hot topic. One area before I go to the last group of machine learning reinforcement, one group that I have seen many resources mention this group as a separate category of machine learning is called semi-supervised. I don't personally believe that it should be mentioned as a separate category of machine learning. Why? Because it is a mixture of supervised and unsupervised, really. It's an extension of them, I would say. And what is it? Here you have input and you have output, but your output is not completely there. Some of your inputs have a target output, a desired output, a labeled output. Some of your inputs do not. So here, where some of the training examples, some of the outputs are what? Missing. That's the major thing here. Not all of your inputs have a desired output. Why? Because as I told you in the beginning of the video, creating these labeled outputs are expensive and time consuming. And in many applications, including computer vision, natural language processing, text processing, and speech recognition, creating these tons and tons of labeled outputs is not easy and not cheap and not fast. So you can just go with as many targeted label data that you have, and the rest of it that there is no label, you try to come up with an idea of how to use them as well as the targeted data. So this method is a mixture of supervised and unsupervised, so we call it semi-supervised learning. But again, since it is kind of mixture of the two major categories, I personally don't believe you should call it a third category. So I just mention it underneath the two of them. The third category of machine learning is called reinforcement learning. And this is something that we humans and the animals have been using and have been training with a lot. What is reinforcement learning? The idea is based on the notion of reward and punishment. You do a good thing, you get a reward. You do a bad thing, you get a punishment. Now, here we just use the word reward because for the sake of machine learning, we can consider punishment like a negative reward. Okay? So the reinforcement learning is this. You are in a situation, you are in a state. You take some action. That action either brings you a reward or a punishment. What would you do? If it gave you a reward, you learn that that's a good thing, so you keep doing it. If you get a punishment, you stop doing it or you try to revise it, right? So the major terms and terminologies is what? You are somewhere in a state, in a position, in a situation. You take some actions. These actions will take you from one position or one state to another state. And this is called state transition, right? Like, for example, if you are playing chess, if you are in cell, for example, A3, and you take a straight move forward, you go to cell A4, correct? So you move from one cell to another, one state to another, and this going from A3 to A4 is called a transition of state. How did it happen? By you taking an action, moving, let's say, your pawn one house forward, correct? So that's an action. And then policy is the set of rules for taking actions. Good? So this is, you keep updating yourself and updating your policies and how to take actions based on whether you got a reward or you got a punishment. And this is how, by the way, many of the computers these days are learning how to play many of these games with us. You see, the computers are getting much better than humans at playing chess, playing blackjack, backgammon, and so many other games, just because we have provided them with tons and tons of different videos of games played by real humans. And they observed that when this human took that specific action, it ended up with something nice or it ended up with a failure. So that's how these machines are learning how to basically behave. And many of the search engine algorithms and so on also work on reinforcement learning, right? For example, if they suggest you something to buy or view or something, and you give them a bad review, right? You see, they always ask for your reviews, for your comments or something. Based on those comments, these machines, these algorithms learn whether they suggest you something or whether they should hide it, correct? And you see that a lot in social media and search engines and so on. So this idea in reinforcement learning is a big thing. There are two major categories of reinforcement learning. One of them is called Markov Decision Process, or MDP, and the other one is called Q-learning. These are two well-known categories. And again, each one needs their own videos or several videos, so I cannot describe them in a few words, but just if I want to give you an idea what is the difference between these two, or what is Markov decision or something like that. So Markov decision means your future is only determined from your current actions. If you have taken an action in the past, that is not going to affect your future. Only whatever decision you make at this moment is going to affect your future. Nothing from the past is going to affect your future. That's called a Markov property or a Markov process, MP. And many of the things in machine learning, many of the processes have such property. Many of them do not. Many of them, the past would come and affect the future. Some of them don't. So Markov decision process and the optimization that is coming with it to solve the problem is called dynamic programming. This is the kind of reinforcement learning based on this Markov property. If your process qualifies for such property, then I can tell you what actions to take, what policies to choose for state transition to come up with what? With some optimal reward, with some maximum reward, because the goal is to what? To maximize the reward. So if I want to get the optimal or the max reward, if my process is a Markovian process, I can tell you what actions to take based on what? Based on an optimization technique called dynamic programming, and give you the best maximum reward that you can take, okay? So this is the Markov decision process. Now, one of the other assumptions that the Markov decision process makes is if you are somewhere in one state at the moment, let's say you are playing chess or something, correct? So if you are in a specific state, then taking an action would deterministically tell you where you would land. So if I am here in this cell, and if I make a decision to move 1 unit forward, then I would definitely land in the blue house. Not everything in problems that you do in machine learning is that clear cut. Many, especially like for the financial or something, you might make a decision to invest so much in some, let's say, business profile or something like that in some company. Now, it doesn't necessarily mean that you will gain this much of benefits or this much of interest or not. Okay, so when the transitions are deterministic, and you can tell definitely, if I give you the state and the action, you can definitely tell me where your next state is or how your transition is going to happen exactly. That is where the Markov decision process can help. If the transition is what? Not deterministic, then that's where Q-learning is coming in. So here, transitions are not deterministic. You might at best have what? Some probabilities. This is what I think. With 50% probability, I end up here, maybe 20% here, maybe 10% here, maybe another 20% here. So if you have probabilities of transitions, not actual crisp deterministic transitions, then you cannot use the Markov process and you have to use a deterministic approach like Q-learning. And in order to solve that, you need to solve something called the Boltzmann equation. And again, each one of these is a separate topic of its own, okay? We'll go through them, but in general, this is the idea of reinforcement learning. So as I told you, reinforcement learning, one real life example of that are the suggestions by the search engine, social media, and so on, the machines learning to play games, and so many other things. This is one application of reinforcement learning in life. By the way, before I jump to the next thing, neural networks can also do or be used for what? For reinforcement learning, right? And one of the areas that you can see, one of the names that comes into play is called deep Q learning. Okay, so they are trying to combine the Q learning with deep neural network, and it shows that it can do Q learning better than just the regular method. The neural network can be trained to do the job of Q learning and solving the Boltzmann equation in a lot better way. So neural networks can also be used for reinforcement learning. Okay, just as a side note. But as I told you, reinforcement learning, you can see it in search engines, playing games, so on, so many things. Unsupervised learning, one real life example of that could be in what we call image segmentation, right? So if I give you an image, this is an application in computer vision. If I give you an image and say, break it down into basically coherent areas which each object or each blob, each segment has a separate meaning. So you see, I gave that image to a segmenting algorithm or clustering algorithm, really what it is. And it has divided it into several different blobs or colors. For example, you see here the red regions are the cars, right? The yellow regions are the buildings. The green regions are the vegetations, bushes, trees, and so on. The pink is the road, right? The sidewalk are in blue, right? The fences are in brown, and so on. You see, and then if there is a black area, there is no label. So that could be sky, but it couldn't label it, right? So it can give you meaningful division of the image into regions that they all belong to kind of same category from the standpoint of us human beings. So that's one of the things that you can do. And I guess I told you about supervised learning. One of the areas is basically recognizing your handwriting, right? So if you write number 4 like that, you can train a neural network to say, hey, that's number 4. If you write 9 like that, still can say this is 9. If you write it any other way, hopefully if you trained it enough, it can recognize your handwriting and tell you what number was it. I have done a project just like this, and for this what you need is called a convolution neural network, CNN. It's not the news channel. Okay, this is a convolution neural network, and this is an area that is used significantly in image processing, computer vision for working with images, convolution neural networks. Okay, so with all that said, the last 2 points are there are a couple of other categories that I have seen in different resources. One of them is called self-learning. Self-learning is an area above I would say reinforcement learning is more generalized version of that, where there is no clear external reward or any advice or anything. You still have to learn how to take an action in an environment, but the notion of the reward is not that kind of clear and nice. Okay, so this is like a hard problem of reinforcement learning. If I don't have a clear reward, what is the function that I'm trying to optimize? How do I change my policies, my action takings to what? To basically solve this problem the best way. Here, I knew my goal was to maximize the reward. But if I don't have any reward, if nobody is giving me any reward or motivation, right, how do I still solve this problem? So this is a very hard problem, self-learning, and I'll see if I can cover anything in that area in this playlist, but I would say that's like a more generalized, harder problem of reinforcement learning, and I don't think you should call it a separate category. And the final thing, another category that I see a lot here and there is called anomaly detection, which is detection of outliers, detection of cases that are out of order, out of ordinary, right? Rare occasions, rare items, observations that can raise suspicions or something. Like what? Like, for example, you probably have seen your credit card company send you an email and say, hey, have you done this transaction? Well, how do they know? Well, they are constantly monitoring all of your transactions. And if they see any transaction that is not a typical thing you do, then they have their own anomaly detection algorithms, which raises a flag, right? A red flag. Say, hey, there is something going on. This person is not doing such a purchase based on what I have seen from their previous transactions, right? So you see that, or you see somebody in a surveillance camera is doing something that is not normal, and then you say, well, that person might be a threat, right? So these are anomaly detections, and anomaly detection, if I want to consider it, I can consider it a classification problem. So either the behavior is what? Either that behavior or what you're doing, that action, whatever it is that a normal action, or is that a what? Is that an anomaly? An anormal, right? Let's say abnormal. So what kind, or that data that I see, is that input? What category it is? So I can say it's a classification problem, and it can be done with supervision or without supervision, right? But in general, again, calling anomaly detection a class of its own under machine learning, I am hesitant to do that. I would like to call it under classifications, and classification could be either supervised or unsupervised. So it's not really beyond the first two categories. That's why I still think we should just say supervised, unsupervised, and reinforced learning are the three major categories of machine learning, and there are all these different algorithms. So hopefully the video was useful to you, and I will see you in my next lecture. Thank you.